Pi equals mc squared.
From the top of the Bohr diagram. It's just facts, you know. And then the top name is the electron name. Then the second is the atomic number. The third is the mass number of the element. And then the fourth is the atomic mass of the element. The amount of electrons in each energy level is, the first energy level there's 2 electrons. The second energy level there's 8 electrons. The third energy level there is 18 electrons. The fourth there is 32 electrons. The fifth energy level there's 50. Big 50. Get that? Then the sixth energy level, there's a big 7-2. Let me draw that out for you. 7-2. You got that? Good.
Game time, baby, let's go!
Valence electrons are electrons in the outermost energy level of the atom, and for some of the transition metals, they can be located in the inner shell electron levels. Not all electrons are valence electrons. There are typically 1 to 8 valence electrons per atom, and when they try to share, give or take electrons, to have 8 valence electrons when they bond.
Game time, baby, let's go!
The octet rule, chemical rule of thumb, helps predict the placement of electrons around the nucleus. Around the nucleus. You get that? Around. They tend to lose, gain, or share electrons until they have 8 electrons in their outer shell. The duet rule, tendency for an atom to acquire, donate, or share electrons to get the electron configuration of helium. Helium, you know the thing in the balloon? Got that? Good. Good. Yes. The atoms that commonly follow the octet rule are carbon. The letter for that one is C. Then you got nitrogen. That one is an N. You get that? Good. Then oxygen. That's the big O. Big O. Then you got the halogens of fluorine, chlorine, bromine, and iodine. Atoms that follow the duet rule, hydrogen, that's the big H. Get that? Big H. Yeah. Lithium. Beryllium. I think that's how you say it. Something like that. And that's it for that one. And there are many that don't follow the rules. Five.
Chemical symbol for the atom for Lewis structures of atoms is you have the chemical symbol, and then it's surrounded by a number of dots corresponding to the number of valence electrons for that atom. Chemical symbol for the element is surrounded by a number of valence electrons, and the ion for Lewis structures of ions. Atoms will gain or lose electrons in order to achieve a stable 8 valence electrons configuration. Negative ions are formed when an atom gains electrons, and positive ions are formed when an atom loses electrons. So, it would be like if I were to punch Chris in the face. He wants to have 8 teeth, so I either have to punch teeth out or add teeth to give him 8 teeth. Isn't that right, Chris?
Yes. Very so much so.
Okay.
You done?
An example is hydrogen has 1 valence electron, so it's an H with a dot.
Done?
Yeah, that's it.
Bond breaking. Like if I break John's face, you know, just punch him a couple times, you might break a jaw. You know, is an endothermic reaction. Energy, the thing that the world revolves around, energy, is absorbed through there. When bond is forming, see that's formed, get it? Is an exothermic reaction. Energy, the world, you know, the whole world revolves around this too, you know, is given out. So you're pretty much, when you're forming a bond, the power plant is sending you energy. You get that? And then when you're breaking a bond, the energy plant over there is taking all the energy back.
Can I drop kick you back?
The turtles are coming!
Oh, where are you going?
I didn't do it. Ionic bonds are made up of positive ions, which are called cations, and negative ions are called anions that are bonded together by electrostatic forces. Electrostatic forces and attraction between electrons. Ions are atoms with a charge. An ionic bond is created when one of the ions donates some of its electrons to the other so that they both have 8 electrons in their outer shell.
A covalent bond is used to describe bonds and compounds that are sharing a pair. See this? Also known as a fruit. Or more than one pair of electrons. A single bond would be easily pulled apart. Almost like you take a piece of Jell-O and then you take another piece of Jell-O and you stick them together and then you pull them apart. That's kind of a similarity there. That's easily. But compared to a double bond would be like tying a piece of string to another piece of, like a piece of yarn, and ripping them apart. A little more harder than Jell-O, but you know, it's still gonna work the same way. Now a triple bond is like taking one piece of iron, welding it to another piece of iron, welding it to another piece of iron, and trying to separate all three into 3 different pieces. It's probably not gonna happen with bare arms. Just saying. A single covalent bond, 2 atoms share exactly 1 pair of electrons. Examples: hydrogen 2, fluorine 2, iodine 2. Double covalent bonds consist of 2 pairs of shared electrons. You know, we reviewed this already, shared. You know, I share my cake with John because he's fat.
Yay, I get cake!
Examples: O2, CO2, and HTCO are molecules that contain double bond. Two bond. Triple covalent bonds consist of 3 pairs. 1, 2, 3 pairs. Are of shared, because I share my cake with John because he's fat.
Yay, cake!
And those examples are C2H2, ethine, and N2 are molecules that contain triple bonds. By sharing electrons, they can both gain an outer shell of 8 electrons, which is what they want. Finn.
Get it up, go.
Yeah!
All metals act the same in the sense that they conduct heat, electricity, and being ductile, which means being able to be formed without breaking, and malleable, which means being able to be shaped easily. Atoms are held together loosely and can be taken away from fairly easily. All metals have that in common. Though not all metals are malleable or ductile. Cast iron, for example, is quite hard but very brittle. But metals are malleable or ductile are so because of the way in which atoms are arranged. In metal, the atoms lie close together, and while they strongly attract one another, may be able to flow past each other while maintaining their proximity. For example, a mosh pit. They're flowing around each other, yet they're still in that one square.
That would be a circle pit, bro. Circle pit.
Oh, sorry. Circle. Mosh pit, circle. I'm sorry. I don't go to them. In metals, the valence electrons of the metal atoms are in fact not bound to their parent atoms, but in fact roam relatively freely between atoms in a sea of sorts. This allows them to travel around carrying electrical current with minimal resistance. This sea of electrons model also helps to explain malleability and ductility. Since the bonds between metal atoms are not forced into specific orientations, the metal atoms can flow past each other without breaking and remain bound to each other. This confirms malleability and ductility. End.
Valence. It's on the chart. We got a chart for the valence electrons here. It goes like this, up and down, and back over. On this side, there's families 3, 4, 5, 6, 7, 8, maybe. I don't know. But then there's over here is 1 and 2. The variable valence goes like this in the middle, and then it goes down like this and back down like this, something like this. This. Those aren't important right now. The important thing is family 8, the halogens, are perfect as they are. They do not need another bonding agent to get 8 valence electrons in the outer shell. Outer shell. Outer? You get it? 7 and 1 would be most likely to bond because they're perfect for each other. 1 is 7, 1 is 8. Or wait, 1 is 7, 1 is 1, which equals 8 for the outer shell. 8. You need 1, 2, 3, 4 on the outer shell. Then 2 and 6 would bond. 5 and 3 would bond, and a couple people from 4 would bond together. And then we got a better chart. Explains it a little bit better. Elements from the opposite ends of the periodic table will generally form ionic bonds, like I just explained, with hydrogen being the exception as it forms covalent bonds. Bonds on the same side will generally be covalent. Alright, the most electronegative is fluorine. The most electropositive is francium. That's a hard word, at least for me.
Francium?
Okay, got something else for you. Carbon, it's right down here. Then oxygen, the big O and the big C, you know, they make a covalent bond of CO2. CO2. That's covalent. An ionic bond is rubidium and fluorine, the big F and the RB. Another covalent bond is hydrogen, the big H again. Here we go with the big H. And then you got chlorine. You know, if you make it into a gas, it's very, very harmful. Could kill you, you know. Not a good thing to mess with. That's about it.
Finger of the good. This right here, this broken spot all around here, it's from me trying to do this hood slide thingamajiggy, and I failed horribly because I broke his car.